Hello students, and welcome to a new chapter about the quantum theory and the electronic structure of the atoms. In 1873, the proposal was that visible light consists of electromagnetic waves. So there are like two different fields perpendicular to each other, the electrical field and the magnetic field. The electromagnetic radiation is energy in a form of waves. So the waves, all electromagnetic waves, travel at a speed of a light which is known to be 3.00 times 10 to the power 8 meter per second in vacuum. So electromagnetic radiation do have energy, and they also have other certain properties that we will be looking at in the next slides. However, it's important to know that all of them travel in vacuum with the speed of light, which is 3 times 10 to the power 8 meter per second. Therefore, we can apply the following equation to all electromagnetic radiation. The speed will equal the wavelength time frequency. So here is an example of the electromagnetic radiation starting from the gamma rays all the way to radio frequency. If you guys take a look, you will see that on the upper part here, I do have the wavelength, and on the lower part here, I have the frequency. When the frequency get higher, which is this end here, it is when I have something like gamma ray, X-ray, UV. These are high energy. And on the right side, with the lower frequency, I have the lower energy electromagnetic radiation. When it comes to the wavelengths, the short wavelengths are associated with high energy electromagnetic radiation, while the long wavelengths are associated with low energy. It's important to know that the visible spectra is right here, higher in energy, which is after violet, ultraviolet, which is after violet, which is the UV, and then X-ray, and then gamma ray, while lower in energy, which is the red end here. So the red is a lower energy than the violet, right? So before the red, we have the infrared, and then the microwave and the radio frequency. Now remember, in our equation, we said that the speed equal the wavelength times frequency. So let's look at that. We said that speed is meter per second. The wavelength here is meter per wave, and the frequency is how many waves are there per every second. So as you can see, I end up having meter per second, which is the unit of the speed. C always equal 3.00 times 10 to the power 8 meter per second. Let's look at this question together. A photon has a frequency of 6.0 times 10 to the power 4 hertz. What is the wavelength of this photon in nanometer? Does this frequency fall in the visible region? And the visible region is anywhere between 400 to 750 nanometer. Now, we said that frequency has a wavelength, has a unit of how many waves per second, and wave per second are always equal to hertz. So hertz is the unit of frequency. They gave me the frequency, but they want the wavelength. So I'm going to use my equation. I know that C equal the wavelength times frequency. C is a value I should know, which is 3.00 times 10 to the power 8 meter per second, equal to the wavelength, which is what I want to calculate, times the frequency, which is given to me as 6.0 times 10 to the power 4 hertz. So all I have to do is to solve for the wavelength, and the wavelength in this case will equal 3.00 times 10 to the power 8 meter per second over 6.0 times 10 to the power 4 hertz. Now remember, hertz is wave per second, right? So the wavelength will be how many meter per wave, but they want it to be expressed in nanometers, so I need to have another conversion factor. And in this conversion factor, I'm going to have a relationship between nanometer and meter. There are 10 to the power 9 nanometer for every meter. So now what I need to do is to log these numbers into my calculator. So the answer will be 5 times 10 to the power 12 nanometer. So definitely not in the visible range. This is a much longer wavelength and therefore way lower in energy. So that should put this here to be a radio wave, which is radio wave where we have a very, very long wavelength and very, very low energy. In the 1900s, Planck said that energy with a light is emitted or absorbed in discrete units that we call quanta. So quanta is the smallest quantity of energy. So you want to think about it the same way we think about atoms. Matter comes from building blocks that we call atoms, and atoms is the smallest building block for the matter. Energy comes in little quantum, which is building block, if you want to say, and the smallest one we call photon, right? So like energy is multiplication of photon, just the same way that matter is multiplication of atoms. He calculated that the energy of any given photon will equal a Planck constant, which is 6.63 times 10 to the negative 34 joule second, times the frequency. So if I don't know the frequency, I can calculate it from the wavelength, because wavelength will equal C over the because frequency will equal C over the wavelength. So what you want to see from this equation and what you want to conclude from this equation is the following. If you see this equation here, you understand that the higher the frequency, the higher the energy. So I can write energy in two ways. I can say energy equal Max Planck constant times frequency. And I also can say energy equal Max Planck constant times C over wavelength. You use this if they gave you frequency, and you use this if they gave you wavelength. Einstein in 1905 saw that when we have something called a photoelectric effect, which is an electron will be ejected from a surface of a certain metal exposed to a light of a minimum frequency or a threshold frequency. So if I give that light to a surface of the metal, I have to have at least that minimum amount of a frequency, then an electron will be emitted. And this is when we started to understand that a photon is a particle of light. So it's like has a dual kind of nature. We can think of it as a particle because of electrons, but it's also a wave because it's an electromagnetic radiation. Energy that we calculate from the previous equation is always representing the energy of one photon. So every time you use this equation, you are calculating the energy for one photon only. What does that mean? If the question is asking about a mole of a photon, then you're going to calculate this and multiply it by Avogadro's number to get a mole of photon. Remember, this equation only for one photon. So the conclusion from Einstein's work then, that light has both natures, the wave nature and the particle nature. Let's look at this question together. When copper is bombarded with high energy electron, X-rays are emitted. Calculate the energy in joule associated with each photon if the wavelength of the X-ray is 0.154 nanometer. What is the energy for a mole of photon? So they want the energy, and energy equals Max Planck constant times frequency. However, they gave me wavelength. So the way I'm going to calculate that, I said energy, see, I'm going to put a Max Planck constant, which is 6.63 times 10 to the negative 34 joule second times, I don't have frequency, but I can calculate it by speed over wavelength. So the speed is, which is c, it's a 3.00 times 10 to the power 8 meter per second. And the wavelength is 0.154. However, wavelength is given in nanometer, and this is here in meter, guys. So I have to convert nanometer into meter, and I'm going to say times 10 to the negative 9 meter. And that is going to give me the energy. So if I do my math correctly, 6.63 negative 34 times 3 to the power 8 divided by 0.154 to the negative 9. The answer will be 1.29 times 10 to the negative 15 joule per 1 photon. Because every time I use this equation, I'm only calculating the energy of one photon. So if they want to have a mole of photons, so what I'm going to say, I know there is 1.29 times 10 to the negative 15 joule for every photon. And now I'm going to do that there is 6.02 times 10 to the power 23 photons for every 1 mole of photons. And when I do my math, the answer will be 7.78 times 10 to the power 8 joules per moles of photons. Okay, so that does conclude this lecture, and I will see you in the next lecture.